So the GSIs have been doing a lot of work getting everyone assigned into sections, and that's the current section times there. If you are looking for a section and you have not got a section assignment yet, is there anyone here who's still in that position? Oh, quite a few. Okay. Well, if you can, stick around a little at the end of the lecture, and we'll talk to you then about seeing if we can find a section time that suits you. Okay. Anything else? Everyone can get on to BSpace. Yeah, you found the site and so on. And let me just remind you, the readings for each week are, you can find them on the section of BSpace, the course website, where it says lectures. Okay, today we're looking at Nagel's article, What is it like to be a bat? This is one of the most influential articles, maybe the single most influential article written in the last 60, 70 years. It's the foundation of most of the work that's done nowadays on consciousness. Even people that don't explicitly cite it, you can see that they have it in mind somewhere. So we'll look at this article today, and on Friday we'll go on and look at Nagel's piece about split brain patients. Incidentally, there are some wonderful videos on YouTube about split brain patients. I'll send round links to one or two of them. So if you can, I encourage you to look at the split brain patient videos. But meantime, let's look at a natural way of thinking about the relation between mind and body. I said last time, the big thing that really puzzles people about mind and brain is when you want to know how it is with someone else, what you're trying to do is get some imaginative understanding of that person. You're trying to get things from their point of view, see what their perspective is. And that really seems important for just the most basic knowledge of what to do about other people, how to be concerned about other people. If you've got a 6-year-old child that's behaving badly to someone else, what do you say to him? Assuming it's Mel, as they so often are. What do you say? You say, how would you like it if it was you? Imagine that was you. Imagine that was being done to you. And the puzzling thing is, you've got that imaginative understanding of someone else's mind. You can get what it's like to be there in someone else's mind. You know you ought not to treat them that way. But then on the other hand, there's knowledge of their brain. And knowledge of the brain seems to be something quite different to that imaginative understanding. So how can these two, your imaginative understanding of other people and your knowledge of what's going on in their brains, how could that be somehow the same kind of thing? And here's a natural way to think about it. You could think, I've got two kinds of spaces here, two different ways of explaining what's going on with other people. On the one hand, I think of them imaginatively. I project myself into their situation. And on the other hand, I can think of them as a physical system governed by laws, a collection of neurons, cell assemblies, all governed by the inexorable laws of physics. And these are two different ways of thinking about the same thing. So you could think of it on analogy with the relation between chemistry and physics. I'm just curious, how many of you guys are science majors? How many humanities? Or non-science at any rate? Yeah. Okay, that's not a bad split. That's pretty good. Okay, well, you can talk me through this because my chemistry, I'm about to tell you the limits of my chemistry, so you can tell me if this is right, what the relation is between chemistry and physics. When the 19th century was becoming the 20th century, around the end of the 19th century, there was a puzzle about the relation between chemistry and physics. And what does chemistry have to do with physics? In chemistry, they were looking at chemicals. They were looking at the laws governing the combination of elements into compounds. They were dealing with puzzles like, how do you differentiate between a compound and a mixture? So they had laws that told you in what proportions two elements would combine when they made a compound. So when elements are combining to yield compounds, they do so in characteristic proportions. And chemistry at that time gave each element a number. It said, that's the valence number of that element. And then you can say, well, I can read off from the valence number of the elements in what proportions they're going to combine to give you a compound. Am I going too fast for you? Okay? So you got laws governing the combination of elements stated in terms of valence numbers. Meanwhile, physics is looking at what the ultimate constituents of matter are. Is matter made of atoms? Can atoms be divided into further particles? And that's just a quite different endeavor. These look like two different enterprises. So what do they have to do with one another? When you were explaining why two elements combined in the proportions that they did to give you a compound, you didn't need to know anything about the atomic structure of matter. You didn't even need to believe the atomic theory of matter. Indeed, lots of influential physicists at the end of the 19th century did not believe the atomic number of theory of matter. You could do pretty well as a chemist, even though you didn't know anything about physics. But then there's the breakthrough when you say, chemistry has these laws governing the way elements combine, and I can explain them in terms of physics. The trick is, you can give a definition of valence in physical terms. So, in physical terms, what's the valence of an element? It's you got the atom. You've got atoms of that element. You've got an outer ring of electrons, and then you have gaps in that outer ring, and the number of gaps in that outer ring is the valence of the element. That's how it was when I was at school. Is that still correct? It's something like that, right? I think you said I think you guys are all science majors. Isn't that right? Something like that is right, right? Once you've defined valence, it must be right. No, nobody's complaining. Right? Yes? Oh, you mean that is right?
I was just going to say, when I was in chemistry class, it was the number of electrons in the outer shell.
There was a number of electrons in the outer shell, right.
Yeah.
That's right. Very good, okay. We're on the same page. Right. The key point is, you've got this notion of valence that you defined in chemistry. You didn't know anything about physics when you're defining that notion of valence and saying how the elements work. But now you find you can define it in terms of basic physics. And now what happens is you can explain the laws of chemistry in terms of basic physics. It turns out that it's because the atoms have that structure that the various elements combine the ways they do. So you've reduced chemistry to physics. Hence, Rutherford's claim that there is only physics and all the rest is stamp collecting. If you understand basic physics, then you understand the whole of chemistry. All that chemistry adds is a whole bunch of details about how various particular atoms or molecules work. It doesn't add anything deep. It just adds a lot of complexity. So you've explained all the chemical laws in terms of physical laws. And generally, that often works. People say, well, lightning is discharge of electricity. Now, once you get that, you can explain all the phenomena of lightning as electrical phenomena. If you say heat is motion of molecules, then you can explain all the things that puzzled you before about what heat does by saying, well, it's motion of molecules. You can explain it in physical terms. If you have an ordinary cook's understanding of heat, then you know that when you heat water, it boils. Once you've got it, that heat is motion of molecules, you can make sense of boiling in terms of motion of molecules. You can explain everything that you didn't understand before in these more basic terms. Or once you know that water is made of the H2O molecule, you can explain why water dissolves things. You can explain why humans like to drink water. You can explain why water has the boiling point it does, and so on, all in these more basic terms. So phenomena involving heat, for example, get deeper explanations when you explain them in terms of motion of molecules. So if you take something basic, that everybody knows that if you pour boiling water into a glass, then often enough the glass will crack. Well, everybody knows that, but why is that? Well, because it had boiling water poured into it, because heat is motion of molecules. When the water is very hot, well, I don't really have the technical vocabulary to explain this properly, but when water is very hot, all the molecules bustle about at a great rate, right? And the faster they go, the more likely they are to hit a weak spot in the glass at great speed. And the more likely you are, the more likely it is for the glass to crack, right? So it's just speaking as a cook with no notion of the atomic theory of matter. You knew that hot water would cause the glass to crack. But now if you know the physics, you can give a better explanation than you did before of why the glass cracks. You can give deeper explanations. But now how does it go for the mind and the brain? Is it like that with the mind and the brain? So you say, look, just as a physicist can give you an analysis of what valence is or what heat is, so too a scientist can tell you what the experience of redness is. You can say, look, it's the firing of this set of cells in V4. Or you can say, the pain that you feel, that is nothing but the firing of C fibers in your brain. That is what science does, right? That is what science is telling you about the mind. So then you could explain all the facts about human psychology in terms of the more basic underlying physics. Just as you can reduce chemistry to physics, you should be able to talk about the mind to physics. Just as you can reduce chemical explanations to physical explanations, there's the imaginative understanding that we ordinarily have of one another that's so important practically in everyday life. That's the only guide we have as to what to do in everyday life. That's all we have to go on. It is really basic. But we ought to be able to give deeper explanations of that in terms of brain phenomena, if this is the right picture. Yeah? But how could that be right? If you've got an understanding of the physics of water or the physics of any element, then you understand everything about how that thing behaves. But